Hi Year 11, today what we're doing is we're looking at domain, range, even and odd functions. We have all of these syllabus dot points and our learning intention today is to develop an understanding of the domain and range of a function, develop an understanding of odd and even functions geometrically and algebraically. You also have your success criteria there. So when you're not sure how to sketch the graph of a function, you can draw up a table of values first. If you know what its basic shape should be, such as a line or parabola, you can use their properties to sketch the graph. So some key properties are our intercepts of our graph. So what we have is the x-intercept of a graph is the value of x where it crosses the x-axis. Oh my gosh. So our x-intercept is over here, and how we find our x-intercepts is it's when y equals 0 or our function equals 0. So to find our x-intercept, we let y equal 0 because it's at y equals 0, which is along our x-axis. Now, our y-intercept of a graph is the value of y where the graph crosses the y-axis. So up here is our y-intercept, and it's when x equals 0. So to find our y-intercept, what we do is we let x equal 0, or we can find f of 0. The solutions of f of x equals 0 are also called our zeros of the function, as they are the values of x for which f of x equals 0. So when we're finding our x-intercepts, they are also called our zeros of our function. So for example 1, we want to find the x and the y-intercepts of the function fx equals x squared plus 7x minus 8. So for our x-intercept, what we do is we let f of x equal 0 or y equals 0. Okay, but because we have f of x, we're going to let that equal 0 today. So we have f of x equals our x squared plus 7x minus 8 equals 0. What we need to do from here is we need to factorize this quadratic. So when we factorize, we're left with x plus 8, lots of x minus 1 is equal to 0. So x, when we solve, is equal to minus 8 and 1. This means that therefore our x-intercepts equal minus 8 and 1. For our y-intercepts now, what we want to do is we let x equal 0, or what we do in this case, because we have f of x, we are going to find f of 0, which is really just letting x equal 0. So to find f of 0, what we'll have is we have 0 squared plus 7 lots of 0 minus 8, which when we put that into our calculator, we get that it equals negative 8. So therefore, our y-intercept is equal to negative 8. Okay, moving on, we have our domain and range of the function. So the domain of a function y equals f of x is the set of all x values for which the function is defined. So it's all the values that x can be. Our range of a function y equals f of x is the set of all y values for which f of x is defined. We can describe the domain and range using words, inequalities, or interval notation. As long as we describe the domain and range correctly and accurately, it doesn't matter which notation we choose. So an example of words is all real x. An example of inequalities is y is greater than or equal to 0, or 0 is less than x is less than 2. An example of interval notation is negative infinity to infinity. Now, generally, we want to use our interval notation. Ideally, that is what you will see most of the time, but sometimes you'll see words and sometimes you'll see inequalities, and we have to be able to go between the three. So with interval notation, it uses square brackets to include the end values, and it also uses round brackets to to exclude the end values. So what we have here is if we have a square bracket A, B, square bracket, it means the interval is between A and B, including our A and our B. If we have round brackets of A and B, it means the interval between A and B is excluding A and B. If we have a square bracket A, B, a round bracket, it means the interval is between A and B, including A, because we have our square bracket there, but excluding B because it has a round bracket touching it. If we have a round bracket A, B, a square bracket, it means the interval between A and B excluding our A, but including our B value. Now, our most common domain and range for some of our functions is negative infinity to infinity, which means that the intervals is between negative infinity to infinity and includes the set of all real numbers, and we use this R to talk about our all real numbers. Another piece of information is the symbol U is for union, and it stands for the joining of two separate parts. What we want to do here for our second example today is to write each inequality in interval notation. So if we have x is greater than 1, it's excluding 1, so we want to do a round bracket, and it's x is greater than 1, so every value larger than 1, so all the way up to infinity. Now, when we have x is greater than or equal to 0, that means it's including our 0, and it's greater than or equal to, so it's going all the way up to infinity. If we're talking about all real numbers y, that's our negative infinity to infinity. If we have 1 is less than y is less than 5, it is excluding 1 to 5 with our curved round brackets there. If it's negative 3 is less than or equal to x is less than or equal to 2, it's our square brackets because it's also equal to 3 and equal to 2. So it's all the values between minus 3 and 2. And if we have minus 2 is less than y is less than or equal to 3, it's excluding minus 2 but including 3. So we have our square bracket there. Now, what we're going to do for example 3 is we're going to find the domain and range of each function. So what I've done here is I've picked some of our key functions that we need to know about. Our top 3 are the ones that we'll be doing in this topic of functions and graphs. And the other ones we see a little bit, but we'll investigate their graphs in more detail down the line. So if we have a linear function, now when we're talking about a linear function, it is a straight line graph. So if we're talking about y equals x, it's our positive straight line linear function that goes through our origin, and for every x value, it corresponds to the equal y value. So thinking the points 1, 1, 3, 3, minus 5, etc. So we're drawing a nice straight line with arrows and our y equals x. Now, when we're talking about our domain, we are talking about what x values we can have. Because this arrow extends all the way on, it means that our y equals x has a domain of negative infinity to infinity. So it will work for any value of x. Our range is what our y values can be. So looking at our y values on our graph, what we have is it's again going on and on and on forever. So it's going to be from negative infinity to infinity. Now, any linear function has the domain and range of negative infinity to infinity. Now, looking at our parabola, we have the parabola y equals x squared. So it has key points at 0, 0, 1, 1, 2, 4, minus 1, 1, and minus 2, 4. So we can sketch our parabola like so with our arrows on the top, y equals x squared. So our domain is talking about our x values that it can be. So all of our x values, like so, and because our arrows just keep on going on and on and on forever, this means our domain of our parabola is going to be from negative infinity to infinity. Now, our range of our parabola is talking about our y values. Now, our parabola only goes from 0 up. So it includes 0. So we do a square bracket at 0 all the way to infinity. Moving on to our next function, it is our cubic function. Now, our cubic function has key points 0, 0, 1, 1, minus 1, minus 1, and the next key points would be 2, 8, and minus 2, 8. So it looks like this when we sketch a cubic function. That's our general cubic function, y equals x cubed. Now, when we're talking about our domain of our cubic function, again, we're talking about all the x values it can be. So this is going on and on and on forever, all the way out. So it is the domain of negative, we're in highlighter mode, sorry. It's the domain of negative infinity to infinity. And then for our range, again, this is extending on and on and on forever. So it has the range of negative infinity to infinity. Okay, moving on to our exponential function, y equals 3 to the power of x. If you're not sure what this looks like, you could put in some x values. But what we have is when x equals 0, it is at 1. When x equals 1, it is at 3. And we will never get any negative values. So our exponential function looks something like this. That's very dodgy. Let me just do that again. So it's never, what's going on? Going to go below our x-axis with an exponential function. So this is our function y equals 3 to the power of x. So what we have here is we actually have an asymptote. At y equals 0 on our x-axis. Okay, so all of the x values that our function can be is every x value because it goes on and on forever. So our domain is negative infinity to infinity here. And our range is what y values we can have. So our range is not including 0 because we have an asymptote at 0 all the way up to infinity. Our next function is a hyperbola. Now, a hyperbola has asymptotes on both axes. So at x equals 0 and y equals 0, we have our asymptotes. Again, if you're not sure how to sketch this, what you can do is you can put in a little table of values. Okay, but what we have happening is it occurs, it looks a little something like this. Just a rough sketch is totally fine for today's lesson. Okay, that is what our hyperbola looks like. Y equals 1 on x. So what we can see is that for our domain, it exists for all of our x values apart from 0 where we have that asymptote. So how we write this is we write that it works from negative infinity to 0, but not including 0, and it works from 0 to infinity. So what we do is we use our union symbol, which is just a U, to put our two parts together. Now, our range is the exact same. It occurs for every y value apart from 0. So we have that it's negative infinity to 0 and 0 to infinity. Now, our square root relation, we haven't really seen or investigated these in stage 5, like year 10 maths, but what we have with these is we have what can x not be. So with our y equals the square root of x minus 1, we have that x minus 1 cannot equal a negative. So what we have is it cannot equal, it can equal 0. And what that does is that helps us to find out where it is at 0. So if we go x equals 1 then, so what we get is we get that it occurs at this point here. But we can't have a negative under our square root. So it's not going to work for any smaller x values. So what that means is our domain is going to be from 1 onwards. And that's all that it works for. So whatever x equals, that affects our domain. Whoops, that's meant to be a 1. To all the way up to infinity. Now with our range, it only works from that x-intercept upwards. So that means our range is going to be from 0 to infinity. Now with this function, if we were to plot some things, if we were to substitute in 2 in here, we'd get the square root of 2 minus 1, which is 1. And then at 5, we get that it's at 2. So if we substitute in some points, we can sketch our square root relation like so. I hope that gave you a good idea about domain and range. If in doubt with domain and range, sketch a little graph to work out what our x values can be. Remember that our x values is our domain and our range is our y values. Okay, moving on to our increasing and decreasing graphs now. So when we draw a graph, it helps to know whether the function is increasing or decreasing on an interval from left to right. So if a graph is increasing, what we have is that y increases as x increases and the graph is moving upwards. What we also have is that the gradient of our, if we were to draw tangents on this, is positive. So we're going up and we're positive from left to right. Okay, our decreasing graphs we have is if a graph is decreasing, then the y decreases as x increases, and we have that the curve moves downwards. So we have that the gradient of these curves are negative if it's decreasing. Now for our example, we want to state the domain over which the curve is increasing. So our curve on our first function here is increasing from 3 all the way up to infinity. So we can write our domain this is just a little sentence. Domain over which the graph is increasing is from 3 to infinity. Now it does not include 3 because at 3 it is neither increasing nor decreasing. So we do our curved brackets, and it's from where x is greater than 3 if we wanted to write it as an inequality. Now for b, we have our domain over which the graph is increasing. So it's increasing from negative infinity to 0, and then it's increasing again from 4 to infinity. So how we write this is we do our negative infinity to 0, and then we do that union symbol again because we have another part, and it's from 4 to infinity. If you wanted to write this as an inequality, you would write it as x is less than 0 and x is greater than 4. Now the last thing that we are learning is about even and odd functions. So even functions have graphs that are symmetrical about the y-axis. The graph doesn't change when it's reflected in the y-axis. The left and right halves are mirror images of each other. This means that the value of y is the same for x equals a and x equals negative a. So what we have is our values are going to be at the same point, as you can see on the graph. So if we were to fold our graph in half about our y-axis, it would be a mirror image of itself. Now, a function is even if f of negative x is equal to f of x for all values of x in the domain. This is very important as we use this for our proof. So what we want to do is we want to show that f of x equals x squared plus 3 is an even function. How we do this is we find f of negative x first. So we'll have negative x all squared plus 3. Now, negative x all squared is equal to positive x squared plus 3, because anything that's negative squared is a positive. Now, what we will notice is that our f of x, I might use a different colour, our f of x is x squared plus 3. So what that means is that our f of negative x is equal to our f of x. And so therefore, f of x is an even function because this property is true. Is an even function as that property of f of negative x is equal to f of x. Okay, so because that works, it means it's an even function. Now we also have odd functions. So odd functions have graphs that have a point of symmetry about the origin. So here is our origin. The graph is rotated 180 degrees about the origin and gives the original graph. So if you pick up your paper and rotate it 180 degrees, you would have the graph looking the exact same as it did. What this means is that the values of y are the same but opposite in sign for x equals a and x equals negative a. So we have that they're the same but in opposite signs in these points. Now our property for an odd function is that a function is odd if f of negative x is equal to negative f of x for all values of x in our domain. Looking at our example on the next page, we want to show that f of x equals x cubed minus x is an odd function. So the first thing we do is the same thing we did for our even functions. We find f of negative x. And so this is equal to negative x cubed minus negative x. Now, anything that is cubed stays the same sign. So that means that negative x cubed is just negative x cubed. And then we have a negative times negative x to make plus x. What we want to do for our odd function is we now want to factorize out the negative. So when we factorize out the negative, what we get is we get x cubed minus x. And what we want is we want that our x cubed minus x is what our function is. So that we have f of negative x is equal to negative f of x, like so. And this is the property for our odd function. So what we do is we write, therefore, f of x is an odd function as f of negative x equals negative f of x. Now, our last example we have is to let f of x equals 2x cubed minus 3x squared plus 4x plus 4. We want to show if fx is odd, even, or neither. Now, what we have here is sometimes functions will be odd, sometimes they'll be even, and sometimes they'll be neither odd or even functions. So what we need to do is our first step to show this is to find f of negative x. So we'll have 2 lots of negative x cubed minus 3 lots of negative x squared plus 4 lots of negative x plus 4. Now when we get a question like this, we find our f of negative x, we do our tidying up. So 2 lots of negative x cubed, when it's cubed it stays the same sign, so it's going to be minus 2x cubed minus 3. Negative x squared is positive x squared, so it's the minus at the front stays a negative. So it stays minus 3x squared. And then we have 4 times minus x to get minus 4x plus 4. Now, when we do this, what we want to do is we want to, in order to show that it's odd or an even or neither, we need to check that it's whether it's even and odd. So we always check our even first. So we check our even functions, and if it's even, we want that f of negative x equals f of x. So does f of negative x equate or is equal to our f of x, which is 2x cubed minus 3x squared plus 4x plus 4? No, it does not. So what we have is that f of negative x does not equal f of x. And so therefore, we have that f of x is not an even function. As f of negative x does not equal f of x. Okay, we always check even first. Now what we do is we check our odd functions. So checking our odd functions, what we have is that f of negative x wants to equal negative f of x. So what we have is that f of negative x is equal to, we want to factorize out a negative, so we'll get negative lots of 2x cubed plus 3x squared plus 4x minus 4. And what we want, if it's an odd function, what we have in the brackets should be equivalent to our f of x, which it is not. So that means we'll have negative, it does not equal negative f of x, because that bracket is not negative f of x. So what this means is that f of x is also not an odd function, as our f of negative x does not equal our negative f of x. So this means that because it's not odd and because it's not even, f of x is neither an even or odd function.